Have the earthquakes gathering along one of Earth's fastest-moving plate boundaries become more than another routine burst of seismic unrest? Are these repeated magnitude 5 class earthquakes simply another reminder that the Tonga Trench is among the most active seismic regions on the planet, or are they the kind of escalating sequence that deserves far closer attention? When memories of the powerful 2021 magnitude 8.1 earthquake remain fresh among seismologists, every new cluster of moderate earthquakes inevitably raises another difficult question. At what point does an ordinary swarm begin to resemble the opening stages of something much larger? Those questions have returned with renewed urgency after a remarkable burst of seismic activity developed along the Tonga Trench in the South Pacific. Within a relatively short period, at least 11 earthquakes ranging from the upper magnitude 4 range into the magnitude 5 range struck near the convergent boundary where the Pacific Plate plunges beneath the Australian Plate. According to earthquake monitoring agencies, the sequence included several earthquakes measuring magnitude 5.0 or greater, while additional magnitude 4 earthquakes filled the intervals between the larger events. The clustering occurred along one of the most rapidly converging plate boundaries on Earth, a region capable of producing some of the largest earthquakes ever recorded. At first glance, the pattern immediately attracted attention because of its location. The Tonga Trench has long been recognized as one of the world's premier megathrust environments. Stretching for more than 1,000 miles, or over 1,600 kilometers, it forms an immense scar across the southwestern Pacific Ocean, where the Pacific Plate descends into Earth's mantle at extraordinary speeds. In certain sections of the trench, convergence approaches nearly 4 inches each year, or roughly 100 millimeters annually, making it among the fastest subduction zones anywhere on the planet. That rapid convergence is not merely a geological curiosity. Every year, the plates continue moving, despite appearing motionless to observers at the surface. Enormous sections of crust grind, bend, compress, fracture, and occasionally lock together. Stress accumulates continuously over decades and centuries before eventually being released through earthquakes, ranging from imperceptible microquakes to colossal megathrust events capable of generating tsunamis that race across entire ocean basins. The recent sequence unfolded in an area already familiar to earthquake scientists. Maps produced by the United States Geological Survey and other international monitoring agencies show the new earthquakes concentrated close to the trench itself, generally following the plate boundary where previous large earthquakes have repeatedly occurred. While individual magnitude 5 earthquakes are relatively common in this part of the Pacific, the appearance of multiple events clustered closely in both time and space naturally draws scientific interest. Even so, history offers an important reminder against reaching premature conclusions. Earthquake swarms occur frequently throughout the Tonga subduction system. Many begin with several moderate earthquakes before gradually fading away over the course of days or weeks. Others persist longer while migrating along sections of the plate boundary or through the descending slab. Most ultimately conclude without producing a major earthquake. That distinction is essential because earthquake swarms and foreshock sequences often appear nearly identical during their earliest stages. Scientists cannot determine with certainty whether a cluster of earthquakes represents ordinary stress adjustment or the opening phase of a much larger rupture until after the sequence has evolved. An event identified afterward as a foreshock becomes known by that name only because a larger earthquake eventually followed it. Before the main shock occurs, there is usually no definitive way to distinguish a foreshock from thousands of other earthquake swarms that never escalate further. This uncertainty explains why every active swarm receives careful scrutiny but rarely prompts immediate predictions. The current sequence has revived memories of the remarkable events that unfolded during the year 2021. During that period, increasing seismic activity developed along portions of the Kermadec-Tonga subduction system before culminating in one of the largest earthquakes recorded anywhere in the world during that year. The sequence eventually produced a magnitude 7.4 earthquake that occurred shortly before an even larger magnitude 8.1 megathrust earthquake ruptured the plate boundary. Because the magnitude 7.4 event preceded the largest rupture, it is now classified as a foreshock. Yet before the magnitude 8.1 earthquake occurred, there was no certainty that the earlier earthquake represented anything more than another major event within an already active subduction zone. That historical example understandably influences present-day discussions. Whenever multiple magnitude 5 earthquakes begin clustering near the Tonga Trench, comparisons with the 2021 sequence naturally emerge. The resemblance, however, should be treated carefully rather than dramatically. One important similarity involves the increase in seismic activity before the 2021 main shock. Another involves the concentration of earthquakes near the plate boundary itself. Yet similarities alone cannot establish that history is repeating. The overwhelming majority of earthquake swarms never culminate in a giant earthquake. That reality forms one of the greatest challenges facing earthquake forecasting. Across the globe, scientists have examined countless swarms occurring along subduction zones in Japan, Alaska, Chile, Indonesia, New Zealand, the Aleutian Islands, and Tonga. While some of these sequences eventually preceded large earthquakes, far more gradually diminished without any major rupture. Statistical analysis consistently demonstrates that most earthquake swarms are not followed by devastating megathrust earthquakes. Consequently, the presence of repeated magnitude 5 earthquakes should not automatically be interpreted as evidence that an earthquake exceeding magnitude 8 is imminent. Instead, each new earthquake contributes another piece to an evolving scientific puzzle. Researchers begin examining several key characteristics almost immediately after a swarm develops. They analyze whether the earthquakes remain tightly clustered or begin migrating along the fault. They compare focal mechanisms to determine whether the earthquakes indicate compression consistent with megathrust motion or whether they reflect internal deformation occurring inside either tectonic plate. They monitor changes in earthquake depth. They evaluate whether rupture areas are expanding towards sections believed to remain strongly locked. They assess whether the sequence displays accelerating energy release or simply fluctuates within expected background behavior. Each of these observations contributes to understanding whether the swarm reflects localized stress redistribution or broader changes occurring along the plate interface. Location is particularly significant. The Tonga Trench represents more than a simple line on a map. Instead, it forms part of an exceptionally complex tectonic environment where several geological processes operate simultaneously. The Pacific Plate descends westward beneath the Australian Plate while undergoing intense bending near the trench. As the plate begins descending into the mantle, enormous stresses develop both within the slab itself and along the contact separating the two tectonic plates. Earthquakes therefore originate from several different environments. Some occur directly on the megathrust interface where the plates remain locked together. Others develop inside the descending Pacific Plate as it bends and fractures under increasing pressure. Additional earthquakes occur within the overriding Australian Plate as crustal rocks respond to continuous compression and deformation. From the surface, these different earthquake types may initially appear similar, yet scientifically they represent very different physical processes. Determining exactly where each earthquake originated therefore becomes one of the highest priorities following the onset of any swarm. Depth measurements provide valuable clues. Shallow earthquakes occurring near the megathrust interface may indicate ongoing adjustment where the plates interact directly. Intermediate depth earthquakes occurring farther within the descending slab often reflect internal fracturing rather than slip occurring along the plate boundary itself. Deep earthquakes, sometimes extending hundreds of miles below Earth's surface or several hundred kilometers, represent yet another entirely different mechanism associated with mineral transformations and extreme pressures inside the sinking slab. Without understanding these distinctions, interpreting an earthquake swarm becomes far more difficult. Modern seismic networks therefore combine information from hundreds of stations spread across the Pacific Basin to refine earthquake locations as additional data become available. Initial solutions frequently improve during subsequent hours and days as more seismic wave arrivals are analyzed. This continual refinement often changes scientific interpretations of an unfolding sequence. Another reason the Tonga Trench commands worldwide attention lies in its extraordinary earthquake history. Few places on Earth produce large earthquakes as frequently. Throughout the 20th and 21st centuries, numerous earthquakes exceeding magnitude 8 have ruptured different sections of the Tonga and neighboring Kermadec subduction zones. Historical records reveal repeated giant earthquakes capable of generating destructive tsunamis while releasing enormous amounts of accumulated tectonic energy. Unlike some subduction zones, where centuries may separate giant earthquakes, portions of the Tonga region experience comparatively frequent large ruptures because of their exceptionally rapid convergence rates. Yet rapid convergence does not imply that every active period culminates in another giant earthquake. Plate motion supplies the energy continuously, but precisely when and where that energy will overcome friction remains one of geophysics' greatest unsolved questions. Stress accumulates unevenly. Some sections release energy through repeated moderate earthquakes. Others remain locked for decades while silently storing enormous strain. Still others experience slow slip events that relieve stress without producing damaging shaking. These contrasting behaviors can exist along neighboring sections of the same plate boundary, making forecasting extraordinarily challenging. For that reason, scientists evaluating the present Tonga swarm remain focused not simply on the number of earthquakes, but on the evolving pattern they collectively reveal. Each additional earthquake offers another opportunity to determine whether the sequence reflects ordinary background adjustment within one of Earth's most active tectonic systems, or whether it is beginning to display characteristics that differ from the countless swarms that have come before. The answer will depend not on a single magnitude 5 earthquake or even several of them, but on the broader evolution of the sequence during the days and weeks ahead. Despite the uncertainty surrounding the present sequence, one fact remains beyond dispute. The Tonga Trench occupies one of the most energetic tectonic environments anywhere on Earth. Few plate boundaries experience such rapid convergence, and few are capable of releasing so much energy over such a relatively short geological timescale. Every year, the Pacific Plate continues its relentless descent beneath the Australian Plate, carrying vast sections of oceanic crust into the mantle while simultaneously reshaping the seafloor above. Although the movement averages only a few inches each year, or roughly 100 millimeters annually, the forces generated are immense because they act across hundreds of miles or hundreds of kilometers of plate boundary. Unlike a single fault cutting through continental crust, the Tonga subduction zone functions as an interconnected mechanical system. Stress does not accumulate uniformly from one end of the trench to the other. Some sections release energy through frequent moderate earthquakes, while neighboring segments remain comparatively quiet for decades. Those quieter areas are often referred to as locked zones because friction prevents the plates from sliding freely. As convergence continues, elastic strain builds within the surrounding rocks until the accumulated stress eventually exceeds the strength of the fault. When that happens, the stored energy is released almost instantaneously, producing a megathrust earthquake capable of shifting enormous portions of the seafloor. Identifying the location and extent of those locked patches has become one of the primary goals of modern earthquake research. Scientists use satellite geodesy, global navigation satellite system measurements, marine seismic surveys, and numerical modeling to estimate which portions of a subduction zone are steadily slipping and which remain firmly locked. Unfortunately, direct observations are far more difficult beneath the ocean than they are on land. Much of the Tonga megathrust lies thousands of feet below the sea surface, making continuous monitoring an enormous technological challenge. That limitation explains why each new earthquake sequence receives such close scrutiny. Rather than examining individual earthquakes in isolation, researchers evaluate how the entire sequence evolves over time. They ask whether earthquakes are occurring along the shallow plate interface or deeper within the descending slab. They compare whether the epicenters remain tightly clustered or gradually expand across a broader region. They also analyze whether successive earthquakes appear to be transferring stress toward neighboring fault segments that have experienced little recent activity. Another important aspect involves earthquake focal mechanisms. Every significant earthquake produces a distinctive pattern of seismic waves that allows scientists to determine the orientation of the fault and the direction in which it slipped. These solutions reveal whether compression, extension, or horizontal shearing dominated the rupture. Along the Tonga Trench, compressional thrust faulting generally reflects movement expected along the megathrust interface, whereas normal fault earthquakes may indicate bending of the descending Pacific plate before it enters the trench. Deep earthquakes exhibiting different mechanisms can signal deformation occurring far inside the sinking slab rather than at the plate boundary itself. The distinction matters because not every earthquake occurring near the trench contributes equally to the loading or unloading of the megathrust. In some cases, earthquakes inside the descending slab may redistribute stress without significantly affecting the locked plate interface. In other situations, ruptures occurring close to the megathrust may alter stress conditions on adjacent sections of the fault. Determining those interactions requires detailed analysis that extends well beyond simply counting the number of earthquakes recorded during a swarm. Researchers are also watching for evidence of systematic migration. If earthquake epicenters begin progressing in a consistent direction over hours or days, the movement may indicate that stress is propagating through connected portions of the fault system. Such migration has been documented in numerous subduction zones around the world. However, migration alone should not be interpreted as a warning that a catastrophic rupture has become inevitable. Many migrating swarms eventually dissipate after redistributing localized stress, leaving the broader plate boundary largely unchanged. Equally important is the rate at which seismic energy is being released. Earthquake sequences sometimes accelerate rapidly, producing progressively larger events over a relatively short period. Others fluctuate without any clear trend, alternating between stronger and weaker earthquakes before gradually declining. Distinguishing between these behaviors requires continuous monitoring because early portions of a swarm often provide too little information to establish a meaningful pattern. Another factor attracting scientific attention is the relationship between seismic activity and the complex geometry of the Tonga subduction zone itself. The trench does not follow a perfectly straight line, nor does the descending slab maintain a uniform angle beneath the overriding plate. Instead, variations in slab curvature, plate roughness, fracture zones, and seamounts carried into the trench all influence how stress accumulates and is eventually released. These structural irregularities can either impede rupture or allow it to propagate across much larger sections of the fault during a major earthquake. History demonstrates that rupture lengths along subduction zones vary enormously. Some earthquakes break only a few dozen miles of fault, or several tens of kilometers, while great megathrust earthquakes may rupture several hundred miles, or hundreds of kilometers, in a matter of minutes. The total length of the rupture, the amount of slip, and the depth at which it occurs largely determine the earthquake's final magnitude and its potential to generate a tsunami. For the current Tonga swarm, none of those larger rupture characteristics have yet emerged. The recorded earthquakes remain moderate in size compared with the tremendous earthquakes the region is capable of producing. That does not diminish their scientific importance, but it does reinforce the need to separate careful observation from speculation. Every active sequence offers an opportunity to improve understanding of one of Earth's most dynamic plate boundaries, yet the available evidence must always guide the conclusions. At present, the earthquakes indicate that the Tonga Trench continues to release tectonic energy within an exceptionally active subduction system. Whether that release represents nothing more than another routine adjustment or the early stages of a more significant episode will depend entirely on how the sequence evolves in the days ahead, making continuous monitoring far more valuable than any attempt to forecast the outcome prematurely.